Welcome to class. Come back. So a couple of bookkeeping things for the class. Does that ever stop? So one is I just posted the first homework with announcement and announcement. So like if you go look at the assignment one, it'll be there. There's links to 4 different notebooks that are hosted on Collaboratory. Like we've mentioned a couple times before. If you just click on the link to any one of these notebooks, it'll open up like the notebook I prepared for this. And then if you just say like, save a copy to my drive, you'll now have your own copy written that you can work in. So you can work in it totally in collaboratory. Or if you don't want to and you want to do something like locally on your machine or whatever, fine, you just have to download it and work on it there. That's fine. That means you'll have to provide your own like Python environment. I haven't provided one outside of collaboratory, mainly because I'm trying to force you to like working collaboratory because it's just so convenient. But whatever. So that works. I think that works really well. So on that note, a couple of things. You've met Alessandro before. He's the head TA of this class. We actually have another TA today, Tanvi. I don't know your last name.
Totally about it.
Yeah.
I'm first year master student in computer science, and I'm from India. I just moved to Utah 2 weeks ago.
So she's going to be helping with grading. So that's Alessandro. He looks like he's feeling better about things. That's why. Tanvi's also going to hold office hours, and she wants to propose a couple of times real quick.
Yeah, I'm free on Mondays and Wednesdays. Either day would be fine, like afternoons or Mondays or Wednesdays. Which one would you prefer? Monday.
Okay, Monday. Okay, Wednesdays. Okay, guys, there's plenty of people who never raise their hands. Okay, so
Do you have like a time?
Anytime in the afternoon, 2 to 3 or 3 to 4.
2 to 3 sounds good.
Okay, yeah, 2 to 3. Mondays 2 to 3. You have a class.
I mean, we have some of us have classes from 3, so.
Sure.
Okay.
Great.
So Mondays 2 to 3.
Okay. Monday 2 to 3, Thursdays 3 to 4. Okay. Good. Thank you. Yes. Oh, right. One more thing about the homework. Once you have completed so there's 4 notebooks, like I mentioned, for the assignment 1. Each one of those is part of the assignment. Once you've completed it, just save it. Make sure it's got all the output in it that you have done, and then just download it and upload it to Campus. That will preserve all the output in the notebook. So when these guys look at it, they will see all the output. They don't have to rerun it. If the output is not there, we'll assume that you didn't do it. So make sure that the output is there after you download. That's the way Python or the Jupyter notebooks work. So that's the way it should work. But just make sure that it's like something where it didn't happen. Like you accidentally clicked the button that said clear all output before you downloaded it. Yeah, and that way we'll just use Canvas for managing all of that. It'll have the times on it for like when you turn it in. Remember, this is due September, was that 14th? By the end of the day. So
we'll probably publish some instructions on how to use.
Sure. So, okay. Any questions on that? All right. So,
Is there a way people who are registered can access the homework?
I didn't understand a single.
Is there a way people who are not registered can access the homework?
You should ask him.
Okay, is the projector not on? Whoops. We'll get this at some point. Okay, so last time we talked a bunch about like just what machine learning is, what a neural network is, just very basic stuff. We started to talk a bit about what ways of classifying and why they might not be as useful or as effective as a neural network. In particular, we started with we started looking at nearest neighbor type classification, and I kind of went really quickly through the end of that. But this class is not about k-nearest neighbors, so eventually I will post these slides, and I'm sorry that I haven't done it yet, but I am really behind on things like that, so eventually they'll be there, you can take a look at them. Also, the first assignment, the first notebook in the first assignment is about implementing a nearest neighbor. There's like instructions in there. It's pretty straightforward, and there's tons of material all over the place about that. But the point is like in the first homework is kind of get some experience kind of building up these different classifiers and how they're different from each other and why you might, like the kinds of things that these different classifiers are learning. So today we're gonna talk about linear classification. Oh yeah, I should have these slides going, sorry. This is what we talked about last time, remember? Bad acting cats and nearest neighbors. But today we're going to talk about linear classification. And the reason we're going to do that is because linear classifiers, like basically, are the building blocks of neural networks. The layers in a neural network are like almost universal. You could look at lots of different things, but they're almost universally linear classifiers that then get followed up by some sort of nonlinearity. So that this isn't just like matrix factorization, but there's like something more going on there. And as a result, you can learn a lot more things than just linear relationships. But there really are just linear classifiers. So we need to know a little bit about linear classifiers to understand what it is we're doing in neural networks. So we're going to spend some time going through that today. We started talking about this particular data set. That's it's pretty useful because it's like real images. There's a lot of them that have nice labels. There's only 10 classes. And there's some that are really different from each other, some that are kind of similar to each other. So it's like just a nice test set. You'll see CPAR10 being used a lot for like testing out basic ideas in neural networks. And this is a set we're going to continue to develop ideas on. So again, there's just a bunch of 32 by 32 RGB images, and they have one of just exactly one of those things in them. So an airplane, an automobile, a bird, and so forth. So linear classification. What are we doing here? So in general, in classification, what we might think about is we have some sort of function that takes our input x, that's our image, and has some parameters to this model. So the last lecture I was using theta, and today I'm using w, but they're both the same thing. These are like the weights or the parameters within this particular model. And then the output of this function, so output of this function on our image x, given the weights, are some numbers that represent the scores we're giving to like each one of these classes. So in CFAR10, we have 10 classes or labels. So how does this work? Well, when we use linear classifiers, this function is just a linear function, meaning like we're doing matrix multiplication here. The weights are just a matrix, and we're multiplying that with the image. Now the image is not originally arranged as a matrix, but we can easily, or as a vector to do matrix vector multiplication, but we can easily arrange it that way just by like flattening it out, just taking each of the columns in the image, for instance, and just making one long vector out of that for all the channels. And like for all the examples that we're going to do here, that's typically what we're thinking of here, is that this x, while it begins life as a tensor, it's really, we're just going to straighten it out, flatten it out to be one long vector. Okay, so like in the instance, so in this instance for the CFAR10 data, the image when it gets stretched out, it's going to be a vector of length 3072. That happens to be 32 times 32 times 3. So that means that our matrix needs to have 3072 columns in it, and it has 10 rows, because in the end, when we do this matrix multiplication, we want to be left with a vector of length 10, right? So you'll get that in this case. We might imagine too, this is still a linear operation. We might just add a constant to this that also is a vector of length 10, number of classes, and this might represent a bunch of things about images in general. This might represent something about where in this 10-dimensional space do I want to kind of start my representation of these types of images, and it's often called the letter, excuse me, B is often used because we call this a bias usually. So it's a bias. It's like the number in the first slot corresponding to like one of the classes. That's like some bias in one direction, some bias in the other direction. So, but the important thing here is like it's just a constant. Like it's just added on to kind of put you somewhere in the space that seemed appropriate. Okay, so that's just, this seems pretty easy, right? This is just linear, this is a linear equation here, or linear function. Matrix times our input plus some constant, the bias. So like I've been saying, here, obviously we had 3,072 values here in this image, but just kind of illustrating the process here. If there were just 4, we would take those and we'd straighten them out, and then we'd have our matrix W. So this is a simple case where we just have 3 classes corresponding to, in this case, cat, dog, and ship. There's some numbers in W already. We do that matrix multiplication. We add the bias, and then we just get some scores. And the top row is corresponding to cat, second row is corresponding to dog, and then the third row is corresponding to ship. So, anyways, just you take any matrix of the right size, any matrix W of the right size, any vector B of the right size, you can do this, and you get some scores given the input. We haven't said anything about whether this is like these scores are good or bad or anything. It's just like you could just do this, right? This is just a linear operation. So, yeah, like this is just like some other way of kind of looking at things and arranging them. It's like we've got all this slide I'm trying to show you right here is that like we had rearranged things here, but you could have just thought of it as looking like that. And the point of this is we're going to see some examples of this in a second, and in your homework you can do a bunch of this. Is like even though I'm only showing 4 numbers here, really like in the actual case of classifying CFAR10, this is going to be a vector of length 30. It's going to be a row vector of length 3072, which can be reshaped back into an image of 32 by 32 by 3, which is what this is showing right here. Like each one of these rows can be reshaped back into the size of the original image. And what's happening is that like you're learning some sort of template for in each row you're learning some sort of template for that particular class. So like the first row in this case is like a template for like the cat category, and the second one for the dog category, and for the ship. And you can actually visualize these things, and you'll see maybe something that looks kind of like that. And like I said, we'll see an example of that here in a second. But when you're in these linear classification, like in all these linear models that we're going to look at, that's basically what's happening. Is we're taking examples of this class, and we're learning. Well, we actually aren't learning here just yet because this is just a setup. Like we're taking this as like a template representing like the prototypical cat or the prototypical dog or the prototypical ship, and we're comparing it. And when you do matrix vector multiplication, you're doing this comparison via what's known as the dot product, right, or the inner product of these two vectors. So it's just the dot product is just like some very principled way of comparing two things. When you think about those vectors, like the angle between them and the differences in distance and magnitude between them. And this is used all over the place. All over the place for comparison reasons. And we're going to see this a lot when we do neural networks, that there's going to be a lot of like dot products going on, and essentially we're going to be comparing, inputs to templates of things and asking, are these similar or not? Questions about that so far? It should seem pretty elementary, like at least the operations going on. Maybe not like when you put them all together, what exactly is going on here, but hopefully when you say the word linear, that makes you feel like, oh, I can do this linear, I can do linear. So like I was saying, in interpreting a linear classifier, we have all these examples of airplanes, and all these examples of automobiles and all these things. And even though we're not talking exactly like how you do the learning just yet, if you do the learning and you learn a template for each of these classes, this is often what you'll get, something that looks a little bit like this. Plane, car, bird, cat, deer, dog, frog, horse, ship, truck. So this should feel a little bit weird to you, but also kind of like cool at the same time. So, let's not start with plane, since plane is like, there's not something totally recognizable there yet, but there is something interesting about that. But so this is again one of these very simple linear classifiers trained on this data set, and here's like the template for the car class that all the other cars get compared against. And there's something car-like about it, right? There's like the hood and the windshield and the front of the car. It's obviously very crude and it's not sharp. But why is it not sharp? Why doesn't this just look like one really sharp car from the automobile? This is car that's automobile from the car class.
It tries to match all the different types of.
It's exactly right. Yes, this has to match every single car it's going to see ever, right? At least what it saw in the training set. So it can't just be some sharp-looking car like what you see up there. It actually has to sort of be able to match them all. So it's interesting that it's sort of symmetric, right? About this x equals 0 axis, or whatever you might call it, symmetric through the middle here. If you were to take this image and you were to swap it like this, it would look pretty much the same. It's interesting that it's probably because you have a bunch of images up there with cars pointing to the left, cars pointing to the right, some in the middle, and so it's kind of got to match all of those. What else, too, about the colors you see in this template?
Windshield is blue.
Yeah, the windshield sort of has a windshield-like tint to it, right? And for whatever reason, it's like a white hood and a red and darkening front end bumper. And this also, I say front end it could be the back as well, although I think most of the pictures we see up there are the front of the car. What would have happened if what would this look like here if, say, all the automobile images were upside down? If in the training set all the automobile images were upside down, what would that look like?
The car would be upside down.
Yeah, the car would probably be upside down. It does depend, the way that we train these things, it does depend on every other thing that's happening, so it might not be exactly upside down, but it's going to be pretty close to that. And yeah, the colors matter too. It's expecting to see sort of a street-like color underneath here, and some other color that's not street-like, I guess, up above, right? And this template is sort of capturing on that. So even though a linear classifier is a pretty weak model, in some sense, it's still pretty strong. This is very data dependent, right? If we had a totally different set of cars, I don't know, say they were all black cars, we would expect this to be black, right? And let's say they were all, I don't know, trucks, every single one was a truck, if they're all pointing in the same direction, you'd get a different template. This is why it's so important to be thinking about what kind of data you're training on, because the only thing it can ever learn to do is, the template it can ever learn to do is, it can only be learned from what's in the data set itself. Okay, so let's move on to something that's also more recognizable. Here's a horse. What's going on with that horse?
I think that it's trying to template both horses facing to the right and left, because you can see 2 heads.
There's 2 heads here, right? This is really interesting, right? And we kind of saw this in the first day when I showed these models that generate pictures of horses. It also had this trouble. It didn't know to only generate 1 head in some sense. It generated 2 heads, but yeah, this has the same thing again, because if you look at all your horse pictures that you have in your data set, lots of horses pointed to the left and a bunch of horses pointing to the right. And this is just like some template that's doing a dot product with, right? So you take one of these pictures of a horse, and you like do a dot product here, you know, it's going to kind of line up with this side. Like there's going to be some discrepancies here that it doesn't line up with, but it's going to line up with a bunch of the rest of it, and that's good. Like that's enough to get it, to hopefully get it over the line and say this is a horse compared to everything else. And again, you see there's like grass-like colors down here, and possibly like sky-like colors up here. Okay. So these start to get really, really bad pretty quick, right? So like here's the cat. There's sort of a cat-like structure here, right? There's like a head and some pointed ears right here. And it's like got that, I don't know, like ginger sort of color to it, I don't know. But interestingly, like everything else around it is pink. So I guess cats are taken, pictures are taken with like pink stuff. But yeah, there's sort of a cat-like structure there. This frog is like some yellow blob with, I don't know, kind of two things sticking out here. So, like impressive in some senses, picking up some of the structure, but you can also see like pretty weak. Like, if we brought in a whole, like if we, like this would do this feels like this would do very poorly at like recognizing a picture of any of these other things if it wasn't very much like the stuff we saw in the training set, right? Because all it has is this like one template to compare itself with. If you think of it as like some vector in 3072 dimensional space, and you come with your image, which is also a vector in 3072 space, and you do a dot product between them, like that's all it can do. That's like the strength of the classifier. And yet, with neural networks, we just build up a whole bunch of these, and we just like one after another after another after another, and it allows it to learn a whole lot more than just like these single templates. But I'm always amused when I see these things. Like the plane, there's like not even a plane anywhere in that picture. But like the sky is blue, there's like clouds, right? And there's like a dark spot where the plane fell through the clouds or something. It's capturing some of the, like maybe like the best way to think about this is that it's captured the statistics of the images that it saw for that class. And of course, when you do this, you're doing the matrix multiplication. So you get a number for each one of these classes. So it takes, you come in with a new image, like a new car, and it's just going to do the dot product with this, and with this, and with this, and with this, and all of them. And that's the vector of length 10 that you're getting at the end. It's one score for each of the classes. Any questions about that? Yeah.
So you probably already said this, but those templates down at the bottom, are those just like the weight vectors as a picture?
Exactly. Sorry, let me say this one more time. This is the matrix W right here.
Okay.
This is the first row from matrix W. It's length 3072, and it's been reshaped to 32 by 32 by 3. Reshaped in the same way that we reshaped our 32 by 32 by 3 input images. It's like reshaping the inverse way of doing that, so that these things line up. Yeah, so this is row 1, 2, 3 on down to 10. Exactly. Thanks for making that clear. Like I said, like even though this is weak, it's still, I like really am amused by this. Like I think this is cool. Like this doesn't take very much work to make something do this, and it's like learned something about the world that you expose it to. There's other ways of thinking about this, and they're all the same way, but just like you can sort of think of this and rearrange the ideas in other ways. So one is that you can think of each of these vectors, these templates, as like pointing in some direction in your space. In your 3072 dimensional space, projected here to 2 dimensions. But you can think of it as like, it's pointing in some direction, like starting from the origin, pointing in some direction. And each one of these is pointing in a different direction. And depending on all the other classes, there happens to be like a plane perpendicular to that vector, like after which well, let me say it differently. You think of all these planes, these perpendicular planes here to your template vectors. They sort of divide up the space into like lots of different regions. And you can think of things of like, if they land in a particular region, like they're going to be classified in that way. That's kind of how like the dot product is working. It's saying like, everything that's close enough to this template vector is going to be classified as one of these things. Everything that's close enough to that template vector is going to be classified as one of those things. And it sort of like divides the space up into regions where classes exist. And that's sort of its job, is to say like, organize the space in such a way that you can do this as best as possible. Lots of intersecting hyperplanes. So, like, what's bad about this? Well, there's a lot of like hard, real-life data sets that this will never do well on, right? So, I mean, this is like very far away from thinking about images, but they're like toy examples that should just help you think about what's going on here. So, think about an example like this where, just two-dimensional, but the class, the classes are divided this way. So like you have first and third quadrant and second and fourth quadrants. Those are the classes. So like, where does a linear classifier, like which vector does it pick as its template for this class or for this class? It's going to have to make a decision. So, like, what's the best it can do in this case? Somebody be brave and throw out a template vector for like the blue class. What's that?
Like diagonal like this.
Yeah, right. So like so blue like this and pink like this, right? Like it's diagonal, but it's going to be pointing in one direction, right? So if it's pointing in this direction, everything that's up here is going to get classified well, because like again, any vector that's up here is really well aligned with it. But everything that's over here, again, it's well aligned with it, but it's well aligned with its negative. So it's going to get the negative value. And you could this wouldn't be linear anymore, but you could say, oh well, I'll just take like the absolute value of that or something and deal with it on a case-by-case basis. But in general, like what's happening is like if you pick it going in this direction, then everything over in this direction suffers, and the same thing happens in this blue class. Okay, what about this second example over here of the like the annulus inside of the space? What's hard about this one for a linear classifier?
Multiple boundaries?
Okay, multiple boundaries. Like maybe another way to say that is the pink class is actually broken up. It's like it's made up of two disconnected pieces. Like the linear classification, I'm talking about, like a dot product doesn't deal with that very well. Yeah, so like you could pick a template vector that was maybe like short, and everything that was like short, but then you'd miss out everything over here, and there's really no way to like deal with. I mean, you get like some sort of like medium-sized template, but again, like it's only pointing in one direction, so it's everything else that's behind it. It's not going to get right, and yeah, there's like no way of like, again, if you think about like the hyperplane, there's no way of like nicely drawing some sort of hyperplane to break up this set. You could transform this set and then try to do this, and then this is like the basis of what are known as kernel methods in machine learning. You transform the set so that this was like that the resulting sets were more linearly classifiable, but as it stands right now, it's not that way. And then finally, this little class example. You got like these three disconnected sets. You might think of this as like some mixture of Gaussians that are centered here, here, and here, and then the rest of the space is the other class. Again, what's hard about this? What's hard about it? Why can't a linear classifier do this?
There's 3 different areas that has to classify for the blue area.
Yeah, like it's gonna have to pick one, like in one direction, and it will get that kind of stuff maybe right, at least nearby in a certain region, but like the rest of it has no chance of. So, yeah, linear classifiers don't do well at nonlinear types of things, right? Each one of these is a nonlinear phenomenon. So, yeah, linear, nonlinear, linear is not equal to nonlinear. And this is a problem, right? So this is where sort of neural networks came into being in some sense. I mean, I don't know exactly the history, but you know, we like the simplicity of what a linear classifier is doing, but can we sort of compose various levels of linear classifiers to deal with issues like this? And it turns out the answer is yes. And we'll hopefully learn a lot about that. Okay, so we have these three ways of thinking about linear classifiers. So, and my personal favorite is always looking at the templates. They're amusing. Okay, so great. Like we know, if we have a matrix of the right shape with a bunch of numbers in it, and a bias vector of the right shape with a bunch of numbers in it, we can produce a bunch of numbers, and we might say that like, we take the largest number that would represent like the largest dot product in the right direction, and say, that's how we classify this thing. But like, how do you tell if it's good or bad? Like this looks bad, right? Like if we do take the largest number as the indication of how we should classify this, then this actually is bad, right? Because dog has been assigned a higher number than cat, and deer has been assigned a higher number than cat, and frog. So like that doesn't seem good. It seems to have done well in this made-up case for the car, and also, well, let's see, because it's the largest, but for the frog, it's negative, right? So like for these three examples, this W doesn't seem to be like a great W. So how do we know if we have a great W or not? The parameters of our linear classifier. Well, that is the next topic here, which is loss functions. So a loss function is a function of our data that tells us, it gives us some indication of how well we are doing. The word loss is kind of funny. It's like, you can literally think of it as like how much we're losing by. We want to always, when we use the word loss or cost, we always want to minimize loss or cost. So if we had zero loss, we'd say like we're doing great. And anything non-zero, we'd say that we have something left to learn. But a loss function is something pretty simple. So if we're given, in our case, in the supervised learning case, where we have some data, x, which like in this case is our image, and some supervised variable, y, and in this case it's which class this is a part of. Then we hope to have a function that for each example, xi, yi, this measures how different our prediction of the class is compared to the correct class. So this is just like abstract form, right? And actually, what this is shown as an average over all of the examples in the data set. So this I range is over all the examples in our data set, and here we've taken an average over all n of them, and that's what we call the total loss. But this is important. There's a primary loss function that gives you the loss for each example, and we typically like average those to give us the loss over the entire data set. So like, what are these loss functions? What do they do? By the way, this f here, this is, I don't know. F is always, we're thinking about this as this linear function, but in general, this could be other types of functions, and this definition would still hold. So here's a loss function. So SVM, support vector machines. If you've taken a machine learning class, you've probably learned about these things. There is a somewhat complicated to look at formula for a loss function here. So I've been using like the word score at times, and there's going to be some S's here. They're going to be shorthand for the output from our function, which is the score. And of course, our function is linear, but more abstractly this applies. But the output of our function, our classification function, is this S. And you have this. So for an individual example, here is a loss function. So let's just take a look at this for a second. So we have this, it's a bit complicated. We have this sum over all j, where j is not equal to the actual class. So j is an index of the class. So, automobile, truck, airplane, whatever. But we don't include our actual class, yi. Remember, we're looking at pairs of examples, xi, yi. Xi is the image, yi is our class. Okay, so if our score that we give this for the correct class is greater than the score we give to one of the incorrect classes, j, plus some number, and this is usually a hyperparameter, but here it's just 1. But if it's greater than the score we give it for the incorrect class j, plus some value, which we call the margin, then we don't assign any loss. So this is the sum over all the classes. So for that particular class, there's a 0 there. There's no contribution to the loss from that. What this is saying is, if our score is large enough, it's at least 1 larger than the score we give to class j, then we're happy here. This means that we're giving us, like in this particular example, the correct score is higher than this incorrect score. And we do this for all of them. So like if this was true for all of the classes not equal to the correct class, then we'd have a 0 right there. However, if this is not the case, if it turns out that the score we're giving to the correct class is actually less than the score we're giving to any incorrect class plus some margin, which here is 1, then we say that the loss is this, which is actually the difference between sj plus 1 and SYI, so the score we get the correct class. And it's like, this is kind of annoying. This is like the way it's always written. Like this, the score of the correct class is like stuck in the middle of it. That way you don't have any dangling negative signs and things like that. But so again, if our score is large enough, if the correct score is large enough, it's larger than the incorrect score for the class j, then we assign no loss. But if it's not, then we assign this loss. And what will this value be? What's the sign of this value in this case? There was 2 answers, and that was it all. It's positive, right? Because
It's penalties.
So in this case, if this is true, this is 0. If this is not the case, and we have an inequality here going, this is less than, and so when we subtract this over this side, we have 0 is less than this term right here. So it's actually positive. But thanks for being brave. Yeah, so it's actually positive. So this is important about loss function and cost functions. We typically want to be assigning positive loss. We don't typically assign negative loss unless it's like a transformation that we know is making things negative, and we're okay with. We'll see that in a second. But yeah, this is the case. So another way to write this right here is just to say that. So this term right here is equal to this. You're actually looking at this this term, and if this is positive, then that's what goes here. But if it's negative, then that condition is satisfied, and then so it's negative, and then you just take the max, which is 0 there. So this is known as the support vector machine loss, or like a hinge loss, actually. And again, it's just saying that like if the correct class, which is along this axis here, is larger than an incorrect class by a certain margin, here 1, then the loss is 0. But if it's less than that, then we assign some sort of loss. And the loss is getting bigger the further away from sj plus 1 that we are. So like the further away we are from actually being larger than it, the more loss there is, the more cost there is. This is really important as we start to learn how to like train these things and learn with them. Questions so far? Yeah, so let's look at this. So if we take these as the scores for each of these classes, we can plug this in over here and see what we get. So we're looking at a cat image, so the correct label is cat. Okay, so in this simple example, we only have 2 other classes besides cat. Here, car and frog. So our sum is going to be over the classes that aren't the cat. So 1 term for the car and 1 term for the frog. So what do we do? So the one for the car, we just fill in the terms here, right? So we take the score for cat. In this row, let's go down here. Oh, I guess hold on a second. This is one, and that's for. Oh, I'm going the wrong direction here. Yeah. So this is for the car class. So we're looking. So J is equal to car. So we look at its score, 5.1. We put it in there. We look at the score we've given to the cat. We put it in there, and that's corrected off, and we have our margin 1. And then we do the same thing when the incorrect class is frog. And just put the same numbers, but the corresponding numbers in over here. And we can do the arithmetic, look at that. This one's positive, so we take that. This one's negative, so we take that. And so the loss here that we've incurred is some number 2.9. Okay? And we can do this for all the examples. For instance, in this case, with these numbers, the loss actually comes out to be 0 because these terms are both negative. So what does that mean in terms of this W? If the loss is 0, what does that mean?
We got the right one.
Yeah, this is good. Like loss 0 means that it means that the score that we assigned to car is the largest one in this case, by a margin of 1, right? So this is larger than this by 1, this is larger than that by 1. And that's the kind of thing that we're trying to do here, is we're trying to not only make it larger, but make it larger by a certain margin. The margin is some way of some sort of confidence that we have in what we're doing here. We can make that margin even larger. It might be harder to learn, but we can make it even larger and try to push scores apart by an even larger number than 1. And frog. So the point of this is that for each of these examples, you can compute this loss. And if we now want to compute the loss over the full data set, all 3 examples here, we just take each one of those individual losses and we average them. So we add them up, divide by 3, and there's the loss that we incurred over the entire data set. So what does 5.27 mean? Well, it's not really clear what it means, but notice that it's not 0. So we're getting some things wrong. And this loss is some sort of expression of how wrong we are over the entire data set on average. Is there a question? Okay. So let's just ask a couple questions here. So question 1, what happens to the loss if car scores change a bit? So these guys right here, what happens to the loss?
Depends on which direction the change opens.
Yeah, just kind of depends on which way it goes, right? So, here where this was non-zero, if we change this kind of either up or down, it's the wrong class, so it comes in as a positive term over there. So this is going to either increase or decrease by the same amount right here. That's how that loss is going to change. How about here, where the score that we've assigned here is comfortably larger than these by 1? What happens if we increase this a little bit? What happens here?
Stays 0.
It stays there. What happens if we decrease a little bit?
Till 3 it stays 0.
Yeah, that's right. So like the next problem we're going to have is when it gets underneath 1 away from 1 of these, which is the largest one. So like you're saying, when it gets down to 3, when it gets just below 3, then we're going to start to see some loss here. Yeah, and similar story applies here. Okay, good. What's the minimum possible loss? What's the maximum possible loss here? What's minimum?
0.
0. 0 is minimum because each one of the terms, its minimum is 0. And so if we got everything, if we satisfied these, well, the condition not up here anymore, but if this was larger than that plus that, then everything would be 0. So what's the maximum possible value?
Max plus 1. Like max of any class plus 1.
Yeah, okay, so like for a given data set, yeah. So like for a given set of scores, that's probably right, yeah. But let's say just like theoretically, like for any data set, what's the maximum we can assign here to the loss? Yeah, there is no maximum. This can just keep getting bigger and bigger and bigger, right? Like this depends on the values of W that we've assigned. We can make that W huge, assign really huge scores, have them be really wrong, and this number can just keep getting bigger and bigger and bigger. So there is no maximum. But important here, the losses assigned here are non-negative, from 0 to infinity. Okay. So when we initialize W, so let's say like we're actually going to be training and we just like assign random values to W, and we're going to start to do some learning on W. So initialization, let's say that it turns out like everything we assign to W is small, so that all the scores are approximately 0. Okay, so all the scores are approximately 0. What's the loss?
0.
Nope.
1.
Good. Good. The margin times number of examples divided by the number of examples, so it's 1. So what's happening in this case is like that's approximately 0, that's approximately 0, then 0 minus 0 is approximately 0, and this is contributing, and then plus 1, so you have 1. So each example is contributing a 1, and when you look at the loss over the entire data set, you sum that over all the examples, that's n times 1, then you average it and divide by n, so it's 1. So the loss is 1 in that case. And this is actually a really good intuition to build, and all the loss functions you might learn is like, what does random look like, or what does like, I don't know, what does like everything incorrect look like? What does everything correct look like? So that you can get some feel, because like again, the numbers themselves don't necessarily mean something. There's not necessarily like a unit on these things that says like, you know, I don't know, meters or something like that. But if you can compare it to say like what does random behavior look like, then you might say, oh look, my loss is comparable with random, so maybe I'm not learning anything. Maybe it's just like random. Okay, what happens if we sum? If the sum is over all the classes? So remember what we're doing is we're looking at these differences, all the incorrect classes compared with the correct class. So what happens if we actually didn't have that not equals to yi and we allowed the correct class in there? What would happen? Say it louder, whoever said that.
Just add 1 point.
Add 1. Yeah, that's right. So that term, like, so that what in that case, j is equal to yi, so these are the same. So that's 0 plus 1, so that's a contributing to 1. So you would, in that case, if we had that, you would never, your loss could never be 0. The smallest it could be would be 1 over n. Or well, 1 in the single data point case. So like it would never be 0. So 0 would no longer, like yeah, 0 would not be the minimum anymore. So like that seems pretty bad. And it's constant, like it's not contributing anything, so that's why we don't include it. What would happen if we used the mean? So here we have, you know, the sum of all these things. What would happen if we use the mean over all of those? So divide by the number of classes minus 1. How would that change the loss?
The trends will be same, I guess the values will be less.
The values will be less by a factor of 1 over number of classes minus 1. But like all the scores would be relative, like they would be ordered relative to each other in the same way. It's just some sort of scaling of it all. So it doesn't change anything. And this is like true in a lot of things that we will do and look at. Like these things just aren't. There's like a lot of transformations to them that would preserve the same sort of learned relationship. Here's another something along those lines. What happens if instead we actually use the square of this max term? What does square map 0 to?
0.
0. So 0 stays the same. What does square do to the rest of the numbers?
So less than 1 decreases, more than 1.
Yeah, so this is a positive value anyways, or non-negative, so 0 or positive. So, and you're squaring it, so squaring preserves the ordering again. So same thing as like with thinking about the mean and the sum. Like, yeah, you get a different value, but everything would be ordered, all the losses would be ordered in the same exact way. So like the details change, but like the overall, you would be making the same predictions. You'd be assigning like the largest value without the square, the largest score, the largest loss, I guess in this case, without the square would be the same. It would also be the largest loss in this other case. It just would be squared. These kind of things are pretty easy to implement. You'll see in the first homework that everything is using NumPy, which is kind of like, which is what's being used here. So no frameworks just yet in the first homeworks. This is just like, let's build up intuition about how scoring and loss functions and gradients and things like that work. But like, here's a really simple implementation. And of course, you could actually do this far more efficient than that if you wanted to. But importantly is this notion of vectorization. So in the homework, it's going to feel pretty pedantic after like the first example. But you're going to be implementing like these scoring and loss functions in non-vectorized ways, which means just like using for loops. And then vectorized ways where there's no for loops. It's basically like the entire operation is happening as like array operations all at once. In any language this is true. In particular in Python this is really true. Python, because of dynamic typing, it has to like, when you run loops, it has to in every loop decide what this variable, what's the type of this variable. So it has to do this introspection of that, and that's a really slow process. And if you have like multiple nested loops, this is like notoriously slow. But NumPy is just like a Python API for like C-level arrays, and if you can get rid of for loops, and you can do your operations as like vector operations. Because like a for loop is basically just like running over all the entries in a vector, or like 2 for loops nested. It's like running over all the entries in a matrix. You can instead do that through like algebraic operations, like dot products, matrix multiplication, then it's going to be way faster. And you'll see this in the homework. This is like something just to be cognizant of. Okay, some more thinking about this. What happens in this loss function if we find a W such that for this data set, the loss is 0. We've perfectly classified everything. We assigned, the highest value assigned was always to the correct class by a margin of 1 in this case. The question here is W unique?
I would say it's not. No.
Why not?
I mean, you could just increase one row for the best scoring ones.
Okay. Yeah. There's probably, let's see. There might be in certain cases where like increasing one row by like a factor might preserve everything still. But then also, that might, because everything's like, you're comparing the scores, if you increase one row, then that would increase all of the scores for just that class. And it might be then that one class now is larger than like the correct class for another, and now you misclassify it. So you're on the right track. It's definitely not unique. You can scale things in a way that preserves the scaling, but that's not the way to do it. What could be done here to give you exactly the same, again, order of scores?
You scale everything.
Yeah.
Scale the entire.
Scale the entire matrix so that every single score is now scaled by that same value. Then if you do that, all of these scores are, the order of all the scores are preserved. And you now have another matrix, you have an infinite number of matrices, W, that have this loss equal 0. So, times 2, times 3, times pi, times whatever. It doesn't need to be positive. If you multiply by a negative number, then you reverse all the orders, and that would be bad. Your highest scoring class would now be your lowest scoring class, and you get everything wrong. But multiply by any positive number, and yeah, this also is a perfect classifier. So
if you module the scalings, that's unique.
Sorry, say it again.
If you module the scaling, is that unique?
I'm not understanding. I'm sorry.
So you say let's group this class 2W and 3W and NW in the same class, and then you say you do a quotient length instead.
Oh, modulo is what you're saying.
Yeah.
Yeah, I guess. So tell me what you're modding by again.
Let's see. C times W. C is the integer.
Oh, you're saying this entire equivalence class is what you're saying.
Yeah. R times.
Yes, exactly. That's good. Yeah. So think a little more abstractly. Like C times W, where C is a positive number. This is the whole equivalence class of the same loss, the same classifiers. That's exactly right. Okay, so yeah, this is just doing the math about if you double things, you get 0 again. So so that's interesting. So now we have this whole equivalence class of matrices that would give you the same classifier. But in some sense, this is bad. So how do we deal with that? We kind of really want to pick out one of these things. We don't want a whole bunch of these things being good. We want to pick out one of these things. And the picking out one of these things is often done through a whole method of techniques called regularization. The word regular or regularize is in math is just really literally to smooth out. So when you regularize a function, you basically, what you're doing is you're allowing there to be higher order derivatives to exist, where they didn't exist before. When we're doing machine learning, it actually just means a whole host of things you would do to the weights of your model to encode prior knowledge you have about the weights or behaviors you want from the weights. And often this leads to smoothing, but not always. But the term regularization is now it's far more reaching here in the machine learning world. So this is our loss function just generally. And a regularization term is something that you add to this loss, so you get a total loss. And again, this is some function whose range is non-negative real numbers, and it expresses some cost that you're incurring through the particular configuration of the weights. And this can be a whole host of things. The lambda in there is known as a regularization parameter or a hyperparameter. And this is something that, if you take some machine learning courses before you, learn how to deal with that and pick a particular value through methods like cross-validation. But the point is you have this term that expresses, some cost for particular configurations of the weights, and you're just the lambda just sort of expresses how much more or less important is it than the other terms in the loss function. So you're adding it to it, it's an additional cost. But let's say you assign a really small value to lambda, so something really small. Then what you're saying is, yeah, the regularization term is there, but it's not really contributing much to the cost. So it's not going to have much effect on it. But if you assign a really large value to lambda, then it's most of the losses is incurred in the regularization, so it's going to really focus on making that smaller. Okay, so there's lots of examples of regularization. The most common ones you'll see are these ones, L2, L1, and elastic net, which I really have no idea how I got that name, but it's just basically an L1 and an L2 term.
So regularization punishes certain things. Would you ever promote something?
Yeah, definitely. It's always punishment though. So like what you're promoting here is small, like, okay, so this right here, L2 regularization, it's just like the sum of the square of all the weights. So like, to make that 0, all the weights have to be 0. Like that's obviously bad. So the interplay between that and your loss function, that's telling you like how well you're doing on the actual problem. Like those two things would balance each other off, but balance each other out. But the thing that's happening here is like it's promoting smaller weights. So you can always characterize it that way. Yeah. So yeah. Those are really simple terms you can add. There's like far more complicated regularizations that we will do. We will learn about dropout, and we will learn about batch normalization. These are wonderful things that really do fantastic regularization in very complex neural networks. But it's kind of hard to say exactly what they're doing like in a simple way. It's not just saying like, let's promote the weights to be small, or let's promote the weights to be sparse, or something like that. They're doing other types of things, and when we get there, we'll discuss it. So why regularize? Again, it's expressing preferences. It's in some sense, like these weight penalizations, they make the model simpler so that it generalizes to tests. So, and there's some improvements that can be had for optimization. So like, if we look at these, if we look at this example, we have two forms of weights here, W1 and W2. And our input there, X, is just a bunch of ones, right? So in each case, the dot product here between these two is 1. So like it's going to assign the same scores to both, 1. So we could have either one, but we want to choose one. So which one does this L2 regularization prefer? Say it loudly. Which one does it prefer?
W2.
Why?
Because this is more spread out.
Okay, well, before we think about it being spread out, what are the values that are here? So R of W1 is what? 1. What's R of W2? Oh, it's something less than 1. It's something less than 1, right? Because like if it wasn't squared, you'd have quarter. You add those all up, you get 1. But then you're squaring that, which makes something less than 1 smaller than itself again. So a quarter of that. So this is much smaller than 1. So actually, it's preferring this. Exactly. And so it's like these kinds of observations that people will say like, oh well, L2 regularization likes to like spread things out. And you can think of it like this. So in this model, I guess I'm not really equation. Okay, I guess I'm not the equation here. So you can think of like F1 as being like the unregularized model learned. But to be able to like do this, like if you're fitting a polynomial into this, to be able to do this, what tends to happen is that you have very large coefficients in your polynomial to be able to like do a really quick turnaround and another quick turnaround. It's just like the way that these things happen. But if you now regularize and you force those weights to be small, but still try to like model the data, then you tend to get something that's not as wiggly. And why that's good is that you're not really trying to model like, in most cases, model all the wiggles. The wiggles are typically noise in the data set. You want to sort of pick out the trends, and so when you now look at the test set, which is represented by these like whitish circles, like you expect to do much better on this test, right? So like, the green is assigning some point here, and that's it's close to for this particular x, that's close, and that's close. But if you were using the blue, you'd be really far off. So like the ideas of regularization are there to express preferences for the way you want the weights to look, and this might come from prior knowledge or prior like understanding of the problem itself. But in particular, it does this very important task of like allowing you to generalize to unseen data. Okay, how are we doing on time? We have 10 minutes, all right. So I'm not going to, we're going to start into this, and then we're going to finish it up and do more optimization next time. But let me just start into this. So that was a particular kind of loss function, hinge loss or support vector machine loss. And this is actually, this is used a ton in modern machine learning, neural network models. Here's something that's used even more for classification, and that is the softmax classifier. So we want to interpret the output from our model, like we showed on the second day, as like an actual probability distribution over our classes. Okay? So how do we do that? So like the scores come out of our linear function like this, right? These are not probabilities, right? They are not all of these numbers are non-negative, and they certainly don't sum to 1. So this is not a probability distribution. So how do we take the scores from our linear function, that output, and turn these into probabilities? So you do this thing up here, which kind of looks ugly the way it's written, but you actually apply exponentials and you divide by the total mass of these exponentials. So let's look at this like this. So the first thing you would do here is you need to make everything non-negative. Okay, if you want this to be a probability distribution, then you need to make all the values non-negative. A very simple way of doing that is just applying an exponential to those, like e to the x, right? So when you do that, then it's mapping the entire range from negative infinity to infinity now to 0 to infinity. So that's good, but so that has one property of probability distributions. That's not quite right. So this operation is this exponential of the numerator up there. So to be a probability distribution, we have to have everything sum to 1. That's very easy to accomplish. We just divide by the sum of everything over all the classes, and now the thing has to sum to 1. So normalizing then is this denominator, which is taking the sum of each of these terms and just dividing by that. Because now when we apply the sum, we get the same thing in the numerator as we have in the denominator, that equals 1. So this is what's called soft max. It's soft because it's kind of like applying the maximum function in some sense. There's like a smooth transition from 0 to 1 rather than like some step function. So you can interpret each of these things then in certain ways. So we said when we apply the exponential, this is like having probabilities, but they're not normalized yet. When we normalize, we get probabilities. We can go back and think about these. We might call these the unnormalized log probabilities, or what's sometimes known as the word logis is used. But they're log probabilities because when we apply an exponential to them, the exponential gets rid of the log, and we're left with probabilities or unnormalized probabilities. This is like very, very, very common in classification problems with neural networks. So so we got probabilities. So now what do we do? In the previous loss function, we try to make the correct score larger than all the other scores by a certain margin. But now we have a probability distribution. Like, what are we trying to do here? Give me some thoughts. What are we trying to do here? So in this example, this is a cat.
So you want cat to be 1?
Yes, you want cat to be 1. And you want the other ones to be 0. Yeah, that's what you want. You want this probability distribution to not look like that. This is bad if this is trying to classify a cat, because this thing thinks it's a car, or at least the way the values are. So a loss function that would, or what we're trying to get the loss function to do here is compare this distribution with the distribution that we really want, which is a certain distribution where all probability is concentrated at cat and everything else is 0. So, I forgot I had a small discussion here before we jumped into that. Before I jump into that, one thing that is typically done to associate it with maximum likelihood estimation, remember we talked about that like in the second day, is instead of looking, thinking about the probabilities, the raw probabilities themselves, we actually take the negative log of these probabilities often. And it will become clear after a while, I think, of working with this. It's like, when you look at it right now, you're like, what? Why would I do that? But there's a lot of nice properties. So, for instance, what's the log of a number between 0 and 1? Yeah, the sign is what? Negative. Yeah, it's negative, right? So within that range is negative. So because we have probabilities here, if we apply a log, we're actually going to get a negative number. And what's the range of that?
0 to 1.
Yeah, so like minus infinity to 0, right? Now if we multiply by negative 1, the negative log, we flip that range over, and now our range goes from 0 to infinity. So we're right back to where we were with the other case, 0 to infinity. That's like a nice place to be. And a transformation like this puts us there. It actually has like more important meaning in terms of maximum likelihood estimation, which we will talk about more when we get more into these issues. But I'll just, in passing, say like, yeah, that's something we might do. But whoops, that should not be a triangle. That should be a rectangle. So we want this distribution to look like that distribution. So we need to compare distributions. How do we compare distributions? Who has, in all of their schooling, ever compared the distributions to each other? Tell me how you did it. Somebody can do it. Say it? Okay. KL divergence. PL divergence. Kolbach-Leibler divergence. What is the Kolbach-Leibler divergence, or KL divergence? It's a horrible set of syllables to say. So you say KL divergence. What is that doing? Well, it's comparing to distributions. How does it happen? Here is how it happens. This is a very strange thing, actually. So this is like probably the most straightforward, or I should say straightforward, the most common way of, it is actually way more straightforward than most ways of comparing probability distributions, but it's the most common way of comparing to distributions. And this is what it is. You're comparing P, you're asking like, what's the divergence of P from Q? So divergence is a weird word here. You might have wondered like, why did it use the word distance or something like this, and we'll talk about that in a second. But you get this, if you're comparing P to Q, P is a probability distribution, Q is a probability distribution, then the way we compare them is we say, so a sum like this with a probability right here, this is an expectation. I don't know if you recall that from probability, but I'm asking like, I'm computing the expected value of this thing right here. The log of the probability of y over the probability of y under the distribution P over the probability of y under the distribution Q. Does anybody like feel weird about this? Because you should. What's weird about it?
Wash bin when small wash bin when it looks like red. What's weird?
I didn't understand that, I'm sorry. Like there's a denominator here.
Which is 0.
That could be 0, right? Yeah, this is bad. Also, this is called a divergence because it's not a distance. What else is like seems weird about this whole term? What happens if you swap the roles of P and Q? It's different, right? Because these things are over here, and if I swap them back, I get a negative sign over here with a log, and then I have a Q out here. Like If I swap the roles of P and Q, I get something totally different. So that's already definitely not a distance, right? Distance has to be symmetric in its two terms, right? So like this is not a distance, and it has some strange properties, and yet this is like the way you compare distributions. And there's like great interpretations of this log term, log P over Q, in terms of like the number of information theoretic interpretations, like how many bits, if the log is a base 2, how many bits do we need in addition to encode something with P over how we can encode it with Q. And then the expectation is the expectation of like the expected number of bits required to do this. And we're not going to go into that deeply here, but just know that lots of these issues get dealt with because of like thinking about limits of numbers. I see that we're out of time, so what I should probably do is just pick up here next time, and we'll go into a little more detail about how this all works with software. First homework is up, so please go take a look. If you have questions, I guess you could use Canvas to do discussions. You know about the office hours now, and yeah, we'll see you on Thursday.